Welcome to The Explainer. Today, we're diving into a technology that could completely revolutionize how we cool our world. We're talking about a way to literally generate cold from a solid piece of metal. And yeah, it might just be the future of refrigeration. Okay, so to get started, I want to put a single number on the screen, 20%. Any guesses what this might represent? That's right. A full fifth of all the electricity we generate on this planet goes into keeping things cool. And that huge energy demand, it's responsible for almost 8% of global greenhouse gas emissions. That is a massive environmental price tag for the air conditioning and refrigeration we all depend on. So this begs a really important question. The technology we use for this, the vapor compression cycle, it's been around for over 100 years. What's actually wrong with it? And why do we so urgently need to find a new way to cool down? Well, the real problem here is the chemical refrigerants it uses, these things called HFCs. They are incredibly potent greenhouse gases, so when they inevitably leak from our air conditioners, they do serious damage to the climate. It's such a big deal that international agreements like the Kigali Amendment are now forcing a global phase-out. On top of all that, the tech is ancient and frankly, its efficiency has pretty much hit a wall. So, if the gas is the problem, what's the solution? What if we could ditch the gas altogether? What if we could get powerful cooling from something completely different, something solid? Well, that is the whole idea behind a family of technologies called caloric cooling. The principle is actually pretty simple, but it's really powerful. You take certain solid materials, you apply some kind of external field to them, and they either heat up or cool down. No leaky gases, just a solid-state material doing all the heavy lifting. Now, it turns out there are four main ways to do this. You can use a magnetic field, an electric field, hydrostatic pressure, or, and this is the one we're going to focus on today, good old-fashioned mechanical stress. Basically, just stretching or squeezing. And it's this last one, elastocaloric cooling, that's really emerging as a frontrunner, mainly because it has the potential to create a really big temperature change. So how in the world does physically stressing a piece of metal actually make it cold? I mean, it sounds kind of like magic, right? But the answer is actually rooted in some really cool fundamental physics. The secret ingredient here is something called latent heat. You can think of it as this huge amount of hidden energy that a material either absorbs or releases whenever it changes its state or its phase. You know, like when ice melts into water. We've all seen this. Picture it. You're heating a block of ice. The temperature climbs up to 0 degrees Celsius. And then it just stops. It sits there, locked at 0, sucking in a ton of heat energy without getting a single degree warmer, until every last bit of it has turned to water. That energy it just absorbed, that's latent heat. Now here's where it gets really interesting. Elastocaloric materials do the exact same thing, but with a wild twist. They don't go from solid to liquid. No, they change from one solid crystal structure to another. And get this, the change isn't triggered by heat, but by pure mechanical force. This right here is the elastocaloric effect. You take one of these special shape memory alloys and you apply stress. You squeeze it. That forces that solid-to-solid phase change and boom, it releases its latent heat and gets warmer. Then, when you let go, the whole process flips in reverse. It snaps back to its original shape, reabsorbs all that latent heat, and in the process becomes significantly colder. Okay, so that's the principle. It's pretty amazing. But how do you actually engineer that into a working device? How do you turn this magic metal into, say, an air conditioner? Well, at a high level, the system works on a thermodynamic cycle that's a lot like the one in your fridge right now. But here's the key difference. Instead of using a compressor to squeeze a gas and make it hot, we're simply applying mechanical stress to a solid alloy. The physics is similar, but the material doing the work is totally different. In a real device, this is built into something called an active regenerator, and it works in a simple 4-step dance. Ready? Step 1, we apply stress to the material, and it heats up. Step 2, a fluid, like water, flows over it to whisk that heat away. Step 3, we release the stress, and the material gets really cold really fast. And step 4, the fluid flows back the other way, picks up all that cold, and delivers it where you need it. You just do that over and over and over again, really fast, and you've got continuous cooling. This all sounds incredible, but there's always a but, right? For any real-world device, there's one giant question: durability. I mean, bending metal back and forth millions of times, that sounds like a recipe for failure. And for a long time, it was this technology's Achilles heel. You see, the first prototypes, they tried stretching the material using tension, and they performed great, but they suffered from metal fatigue and failed after only about 10,000 cycles. That's not going to cut it for an appliance you want to last for 10 years. But then came the breakthrough. Researchers switched to compression, squeezing the material. And it turns out that's way less damaging and can boost the lifespan to over 1 million cycles. And this is just a perfect example of how innovation works. By really understanding the failure, engineers were able to design a completely new device based on compression. And it didn't just solve the fatigue problem, it also achieved record-breaking performance. So, get this. A new prototype has now been run for over 300,000 cycles. And here's the key part, with absolutely no degradation in performance. This is a huge step, and it shows a clear path toward making these things commercially viable. And the performance is just staggering. This device achieved a maximum temperature difference of over 31 Kelvin. For those of us who aren't physicists, that's the same as 31 degrees Celsius. That is some serious cooling power, more than enough for any practical air conditioning or refrigeration you can think of. What's even more impressive might be the power density, basically how much cooling you can get from a small amount of this stuff. It produced a cooling power of 4,400 watts per kilogram. To put that in perspective, that number surpasses all other known caloric devices, no matter what kind of field they use. So, let's zoom out. Why does all of this matter? What's the real-world impact of having a durable, high-performance, solid-state cooling system? Well, let's put it head-to-head with today's tech. Instead of a gas with a high global warming potential, you have an environmentally friendly solid alloy. This means direct emissions from refrigerant leaks are zero. Gone. The total warming impact could be an order of magnitude lower. And maybe the best part, the technology we have now is mature. Its efficiency has hit a ceiling. This new technology is just getting started, with enormous potential to get even better. With its incredible performance, its proven durability, and its undeniable green credentials, elastocaloric cooling is fast becoming more than just a lab curiosity. It's a serious contender. It really just leaves us with one final exciting question. How soon before this solid-state revolution actually arrives to cool our world?